Hey Math 30-1. So we continue our applications of exponential and log functions. This is part 2 of that first PowerPoint lesson. And so we're solving exponential equations where we don't have the same base. Now in this particular case, when you look at this, you say, wow, wait a second, I can use the same base. And you're right, you can. So we'll do this one two ways. If I solve it using our same base strategy, clearly this is a pretty easy question. 2 to the x equals 2 to the 3. Wow, of course, therefore x equals 3. Voila, okay? We know that, but what if we couldn't? What if we couldn't do the same base? Just to show there is another method. How could we use logs? Well, if I take the log of both sides of this question, so if I take the log of the left side and the log of the right side, kind of like taking the square root of both sides or other operations. If I take the log of both sides, I end up with this. And remembering the laws of logs, if I do that, then really that's x log 2 equals log 8. And now if you isolate x, you divide both sides by log 2 and you get your answer. And if you use your common log button on your calculator, log 8 divided by log 2, guess what? It ends up being exactly 3. Well, of course it does, because we already knew the answer was 3. So how is this helpful? We're not trying to complicate something that we knew easily, but we're not going to be able to do it in an easy way here. For this one, you can't solve that by simply putting 12 as the same base. 12 doesn't work. 2 to the what equals 12. It doesn't have a base, and so that doesn't work. There has to be a different way. Well, turns out we take the log of both sides. And if I take the log of both sides, notice I've skipped a step in PowerPoint. It would have started out as the log of 2 to the x equals the log of 12, but using the power law, x log 2 equals 12, log 12, and so we get x equals log 12 over log 2. That's the exact value. That's the exact value of that. Now, if we choose to be approximate, it can be approximately, and we don't want to put that, it's approximately equal to 3.58. So if you want to have an exact value, you got to leave it like that. Okay? And sometimes, most times, on your exams and questions in multiple choice, they want the exact value. Okay, so we need to be able to do that. So if we take 2 to the exponent 3.58, you're not going to get exactly 12. You can try it, but you'll get close to 12. Okay, it won't be exactly 12. All right. Well, that's a pretty straightforward question. What about something a little bit tougher? What if you had 7 to the 1/2 x equals 40? Again, if I could change 40 to a base of 7, I would. This isn't the fastest, that would be the fastest way, but it's not the same base. So I need to take the log of both sides. Using the power rule, that means that I've got a half, right? I've got a half x log 7 equals log 40. You need to solve that for x. So the first thing we do is divide by log 7, right? Or we could multiply by 2, depending on how you want to handle it. We multiply both sides by 2 to get rid of, right? To get rid of that half. And now we'll divide by 7, log 7. So our final answer, exact value, is 2 log 40 over log 7, which is approximately equal to 3.79. Not exactly, okay? What about something a little bit more complicated? What about something like that? What do we do with that? Well, now we're back to logs, and so we want to bring our logs together. So if I bring my logs together, right, I use my laws of logs. So now we might be going back to some of the strategy we used in part 1. Now I get the log. Adding logs comes from multiplying. And so we now think about, well, when I have something log, could I change its form and write it in a better way? So my suggestion would be that you would say, well, now I've got this, so I've really got x squared minus 8x plus 12 is equal to 5 to the 1. So I wrote this as this equals 5 to the 1. So that means that x squared minus 5x plus 7 is equal to 0. I can factor that to be x minus 7, and x minus 1 equals 0. Therefore, x equals 7 or x equals 1. But we need to check. So you could think about your domain, your non-principal values, but restrictions. But I can simply look and say, well, if I plug in 7, I am good. Plug in check. If I plug in 1, that's not going to work. So my final answer is going to be x equals 7. This isn't the only way. You might see in your textbook, and I chose to, and you'll see the PowerPoint kind of override my writing. The other way to do it would be to write it as a log on the other side. So what is 1? Well, it's really the log of 5 to the 1. In the end, you get the same equation, and you get the same answers, and you obviously get that same restriction. What if we had something like 9? Now we're getting to as tough a question as you can kind of be asked. So we're looking at 3 to the x. Whoa, definitely not the same base. So I'm going to have to take the log, and now it's going to get interesting. So if I take the log of both sides, I now have to use my power law, and I get something that looks like this. Now that looks a little ugly. If I were to ask you to solve this question way back in Math 10, you'd say, oh, Mr. K, that's easy. 3x equals x plus 1 times 2. 3x equals 2x. You would distribute the 2, and you'd have 2x plus 2. And then you'd say, oh, I'll collect the x's together. 3x minus 2x equals 2. So that means x equals 2, and you'd be happy, and that would be easy. That's not what you have, because you have these ugly numbers, log 3 and log. So you got this log. Well, you can't ignore the log, but you do have to do the same strategy. You need to distribute the log, and then you need to collect your x's together. So if you distribute the log, you have x log 2 plus log 2, and you now collect your logs together, and you have x log 3 minus x log 2. And personally, if you like seeing it that way, I'll finish up. You factor out the x, and you end up with x log 3 minus log 2 equals log 2, and you divide, and you end up with a final answer that's exactly log 2 divided by log 3 minus log 2. Personally, to kind of draw similarities to what we did here in grade 9 and so on, I personally like thinking about it like this. So if I go back to this question, when I distribute, I put the log out front. And so I think of this as, and the books won't say it, but log 3 x's, that's how many x's you got, equals log 2 x's plus log 2. So I collect my x's together, which means I'm going to have log 3 x's minus log 2 x's. Now I have to put brackets because equals log 2. And so when you factor the x out, you get log 3 minus log 2 equals log 2. So x equals log 2 divided by log 3 minus log 2. Now, it doesn't matter which way you do it. The reason that most textbooks don't show it the way I'm showing you is because this can be confused, right, with a b value of 2, where it's log 2x. And there is a major difference between log 2x and log 2x. So I just think when we first learn this, maybe it's handier to think of it like we did when we did nice numbers that were integers. So whichever way you find better, and you find peace, I'm just going to erase this so you can look back, and whichever way you find better is the way I'd like you to do it. And I can show it both ways in class tomorrow, but most important thing is that in the final, we need to have this exact answer and then that approximate answer, okay? And lastly, This one has obviously a coefficient out front, which is going to complicate it a bit, and it's the toughest question we're going to have. So if I take the log of both sides, I've got to use all my laws of logs. I remember this. If I'm multiplying, I add logs, so that should be the breakdown using the laws of logs. I need to expand out that x plus 6 log 6. This is all good, but there's my x right there. So I expand that one out, and now this is an x term. I need to collect my x's, and I'll take my numerical coefficients all to one side, right? So I take those numbers to one side, I collect my x's to the other side, and I end up with this, which I factor the x out, and my final answer is log 6 minus log 2 over log 18 minus log 6, which is the exact answer, which way cool turns out to be 1. And if you're wondering why, well, you could do it on your calculator, but notice that on the top, log 6 minus log 2 would be 6 over 2, and the bottom would be equal to log 18 divided by 6. Both of those equal log 3. So log 3 divided by log 3 is clearly 1. And if you check back, does that actually work? Yes, it does. Okay, last multiple choice question. If this is true, when y is greater than 0, then y is equal to, and again, this is kind of a benchmark question. You need to manipulate this and solve it for y. Okay, so you use your laws of logs, solve that, manipulate this question so y is by itself, and you should get an answer of D. And now you should be doing, I think it's this one, but I can't remember. Look up and see which question you're supposed to be doing. We are done.